We all know nothing can travel faster than light, but have you ever wondered why? The universe has a built-in speed limit that nothing with mass can break, and the reason behind it is way stranger than you think. In this video, we're going to explore what actually happens when you try to reach light speed, the energy requirements that explode to infinity, the way time itself slows down, and the bizarre physics that makes it all impossible. If you enjoy learning about how the universe really works, hit that like button and subscribe for more physics explanations. Let's dive in. The universe has a speed limit, and you cannot break it. Light travels at exactly 186,282 miles per second. Every photon moves at this exact velocity through empty space, no matter where you are in the cosmos. No matter how you measure it, this speed never changes. But here's where reality bends your mind. This isn't just about light being fast. This is about the deepest law written into the fabric of existence itself. Scientists call it the cosmic speed limit, and it governs everything that moves through space and time. Think about highways for a moment. You can drive 60 miles per hour, maybe 80 if nobody's watching. With a faster car, you go faster. More power equals more speed. That logic works perfectly here on Earth. But physics rips that logic apart when you approach light speed. Albert Einstein discovered this barrier in 1905. His theory of special relativity revealed something shocking. The speed of light isn't just another speed. It's the maximum velocity at which any information, any particle, any object with mass can travel through the universe. Nothing can reach it. Nothing can exceed it. This is confirmed science, tested thousands of times in laboratories worldwide. What makes this speed limit so absolute? The answer lies in how space and time themselves work. They're not separate things. They're woven together into something called spacetime. Light moves through this four-dimensional fabric at exactly one speed, and that speed defines the structure of reality itself. Here's where it gets stranger. If you're sitting still right now, you're already traveling through space-time at light speed. You're just moving through time instead of space. Every second that ticks by, you're racing through the time dimension at maximum velocity. When you start moving through space, something has to give. You begin trading your motion through time for motion through space. Scientists have verified this with atomic clocks. These devices measure time with incredible precision, accurate to billionths of a second. When physicists flew atomic clocks on airplanes in 1971, the moving clocks ticked slower than identical clocks left on the ground. The difference was tiny, just fractions of microseconds, but it was real. It was measurable. It proved Einstein right. The Large Hadron Collider smashes particles together at 99.9999991% of light speed. These particles weigh almost nothing. Scientists pump enormous amounts of energy into accelerating them, yet they can never quite reach 100%. The closer they get, the harder it becomes. The last tiny fraction requires exponentially more energy than all the energy that came before. This isn't because our technology is limited. This is because reality itself draws a line and says, this far and no farther. The speed of light stands as an impenetrable wall, separating what's possible from what will forever remain impossible. But why does this wall exist at all? What happens when you try to punch through it? The answer involves something far more sinister than you might imagine. In 1905, a 26-year-old patent clerk published a paper that destroyed humanity's understanding of reality. Albert Einstein wasn't. Light speed remained constant, always the same, 186,000 miles per second, no matter which direction you measured from or how fast you were moving. This made no sense under the old rules of physics. Einstein realized something radical. What if the speed of light truly never changed? What if this constancy was the fundamental rule and everything else had to bend around it? What if time and space themselves were flexible? His paper introduced special relativity, The theory rested on two simple ideas. First, the laws of physics are the same everywhere in the universe for anyone moving at constant velocity. Second, light speed in empty space is always the same for every observer, regardless of motion. These principles seem innocent. Their consequences are devastating. If light speed is always constant, then time must be flexible. A clock moving past you ticks slower than your own clock. This isn't an illusion. This isn't a malfunction. Time genuinely passes at different rates depending on motion. Einstein called this time dilation, and it's been confirmed by every experiment designed to test it. Space is flexible too. Objects moving at high speed physically shrink in the direction of motion. A spaceship traveling at 90% light speed would be compressed to less than half its original length as measured by a stationary observer. The astronauts inside wouldn't notice anything wrong. From their perspective, the universe outside would appear compressed instead. Einstein derived all of this using nothing more than logic and mathematics. He didn't have advanced technology. He had thought experiments. He imagined riding alongside a beam of light. He visualized what that would look like. The math that followed revealed a universe far stranger than anyone had imagined. The theory sparked controversy immediately. Many scientists rejected it. Time that changes, space that shrinks, these ideas violated common sense. They contradicted centuries of accepted physics built on Newton's laws. How could a patent clerk overturn Newton? But experiments started confirming Einstein's predictions. One after another, tests showed that special relativity correctly described reality. Time dilation was real. Length contraction was real. The equations worked perfectly. Within 2 decades, special relativity became the foundation of modern physics. Einstein's theory revealed that mass and energy are interchangeable. He wrote the most famous equation in science: energy equals mass times the speed of light squared. This equation shows that tiny amounts of mass contain staggering amounts of energy. It explains how stars burn. It explains how nuclear weapons release such devastating force. Yet, the equation also spelled doom for space travel. The closer you approach light speed, the more your energy increases without your velocity increasing proportionally. Something else grows instead. Something that creates an insurmountable barrier. There's a mathematical demon hiding in Einstein's equations, and it destroys any hope of reaching light speed. Scientists call it the Lorentz factor. This single number determines how much time dilation occurs, how much length contraction happens, and most importantly, how reality breaks down as you accelerate. The formula looks simple. 1 divided by the square root of 1 minus your velocity squared divided by light speed squared. At everyday speeds, the Lorentz factor equals 1. Your car traveling 60 miles per hour has a Lorentz factor of 1.000000001, essentially 1. Time dilation at this speed is so minuscule that it's completely undetectable in daily life. Newton's old physics works perfectly fine. Push up to 10% light speed. Now the Lorentz factor climbs to 1.005. Still small. Time passes slightly slower for you compared to someone standing still. But the effect is barely noticeable. You'd need extremely precise instruments to measure it. Jump to 50% light speed. The Lorentz factor hits 1.15. Now things get interesting. For every hour that passes for you, 70 minutes pass for someone at rest. The difference becomes significant. Time dilation starts affecting actual experiences, not just measurements. Accelerate to 90% light speed. The Lorentz factor explodes to 2.29. Your clock runs at less than half the speed of a stationary clock. For every year you experience, more than 2 years pass back on Earth. You're time traveling into the future, whether you want to or not. But watch what happens at 99%. The Lorentz factor jumps to 7.09. For each year you age, 7 years pass on Earth. And here's where the nightmare truly begins. Each tiny increment toward light speed makes the Lorentz factor grow faster and faster. At 99.9%, the Lorentz factor reaches 22. At 99.99%, it hits 71. At 99.999%, 224. The numbers explode exponentially. Add another 9 to that decimal, and the factor doubles again. The graph of the Lorentz factor looks like a calm slope that suddenly becomes a vertical cliff. As your velocity approaches light speed, the curve shoots upward toward infinity. This isn't just mathematical abstraction. This represents real physical quantities going haywire. Everything the Lorentz factor touches gets multiplied by its value. Your momentum gets multiplied. Your kinetic energy gets multiplied. Your resistance to further acceleration gets multiplied. As the Lorentz factor climbs toward infinity, so does everything else. Picture trying to climb a mountain, where each step is twice as high as the previous one. The first steps are easy. By step 10, you're climbing walls. By step 20, you're scaling cliffs taller than skyscrapers. By step 30, the next step is higher than Mount Everest. You can keep climbing forever and never reach the summit because the summit is infinitely far away. That's exactly what happens with light speed. The Lorentz factor guarantees that the final gap between your speed and light speed requires infinite resources to cross, not a lot of resources. Not more resources than humanity possesses, infinite resources, more energy than exists in the entire observable universe. Mathematicians confirm this. At exactly light speed, the Lorentz factor becomes undefined. Division by zero. The equation breaks. Reality itself refuses to compute. The universe is telling you something fundamental. This speed is forbidden for anything with mass. But what physical process does the Lorentz factor actually affect? What real phenomenon does it multiply until everything falls apart? Momentum is about to become your worst enemy. In everyday life, momentum is simple. It's mass times velocity. A bowling ball rolling at 10 miles per hour has momentum. A feather drifting at the same speed has much less. To change an object's momentum, you apply force. Push harder, and the momentum changes faster. This works perfectly at normal speeds. Double your velocity, and you double your momentum. Triple your force, and you triple the rate of momentum change. The relationship is linear, predictable, manageable. Einstein revealed that this comfortable relationship shatters at high velocities. In special relativity, momentum isn't just mass times velocity. It's mass times velocity times the Lorentz factor. And as we just learned, the Lorentz factor can grow without limit. At 90% light speed, your momentum is already more than twice what Newton's old formulas would predict. The Lorentz factor of 2.29 multiplies your classical momentum, making you more than twice as hard to accelerate further. You haven't gained any additional mass, but you behave as if you're more than twice as heavy. Push to 99% light speed. Now your momentum is 7 times higher than classical physics predicts. Accelerating you even slightly requires 7 times more force than Newton's equations suggest. You're becoming exponentially harder to push. This creates a vicious spiral. The faster you go, the higher your momentum climbs. Higher momentum means more force is needed to accelerate you. That additional force makes you go faster, which increases your momentum even more, which requires even more force. The cycle feeds on itself. At 99.999% light speed, your momentum is already hundreds of times what classical mechanics predicted. You've become a massive object in terms of resistance to acceleration, even though your actual mass hasn't changed by a single atom. The rocket engines fire at full power. They produce the same thrust as always, but you barely budge. Here's what makes this truly nightmarish. As you approach light speed, the Lorentz factor approaches infinity. That means your relativistic momentum also approaches infinity. An object with infinite momentum cannot be accelerated any further. You would need infinite force to change infinite momentum, even by an infinitesimal amount. Think of it like pushing a car. At first, The car rolls easily. As you gain speed, air resistance increases. The car becomes slightly harder to push. But imagine if the car became twice as heavy with each mile per hour gained. By 20 miles per hour, it would weigh tons. By 50, it would outmass buildings. By 100, it would be heavier than planets. You would never reach 200 miles per hour because the car would become infinitely massive before you got there. That's relativistic momentum. The closer you get to light speed, the more resistance the universe offers. Not because you're gaining mass in the traditional sense, because momentum itself is increasing without bound. Particle accelerators prove this every day. The Large Hadron Collider accelerates protons in a 17-mile ring. They pump enormous amounts of energy into these tiny particles. The protons get closer and closer to light speed, 99.99991%, but that last sliver remains forever out of reach. Scientists can measure the proton's momentum directly. It matches Einstein's predictions perfectly. The relativistic momentum grows exactly as the Lorentz factor predicts. The particles become harder and harder to accelerate, even though they haven't gained any additional mass. At exactly light speed, the momentum of any massive object would be literally infinite. An infinite quantity cannot exist in reality. The universe draws a line. You cannot cross this threshold. The laws of physics actively prevent it by making acceleration progressively more difficult until further acceleration becomes impossible. But momentum isn't the only thing that explodes as you accelerate. Something even more fundamental begins spiraling out of control. Energy equals mass times the speed of light squared, and this equation ends all hope of light speed travel. Einstein wrote this formula in 1905, 3 symbols that rewrote reality. The equation reveals that mass and energy are 2 forms of the same thing. Convert a tiny bit of mass, and you release staggering amounts of energy. 1 kilogram of matter, if completely converted, releases 90 trillion joules. That's the energy of 20 megatons of TNT. This is why the sun shines. Every second, the sun converts 600 million tons of hydrogen into helium. About 4 million tons disappear completely, transformed into pure energy. That missing mass powers all life on Earth. The sun has been burning for 4.5 billion years and will continue for billions more, all from converting mass to energy. Nuclear weapons work the same way. A tiny fraction of uranium or plutonium converts to energy during detonation. Less than 1% of the bomb's mass actually transforms. That small fraction levels cities. The equation is that powerful. But the equation works in reverse too. Energy can become mass. This happens constantly in particle accelerators. Scientists collide high-energy particles and watch new particles materialize from pure energy. Quarks, muons, even antimatter, all created from kinetic energy transforming into mass. Here's where this destroys space travel. As you accelerate a spacecraft, you're adding kinetic energy to it. That energy has to go somewhere. At low speeds, it becomes velocity. The ship goes faster. But at relativistic speeds, the added energy increasingly becomes inertia instead of speed. The ship becomes harder to accelerate, as if it had gained mass. Physicists used to describe this as relativistic mass increase. Modern physics doesn't use that term anymore because it's misleading. Your rest mass never changes. A 1,000 kilogram spacecraft always masses 1,000 kilograms when measured at rest, but its inertia, its resistance to acceleration, absolutely does increase. Calculate the kinetic energy of a 1,000 kilogram spacecraft at 50% light speed using Einstein's formula. The answer is 15 trillion joules. That's the energy of 3.5 megatons of TNT. Just to reach half-light speed, you need the explosive power of 70 Hiroshima bombs concentrated into moving your ship, pushed to 90% light speed. The kinetic energy soars to 130 trillion joules. You've jumped from 3 megatons to 30 megatons equivalent. 10 times more energy for moving from 50% to 90%. The energy requirements are accelerating faster than your velocity. At 99% light speed, you need 630 trillion joules. That's 150 megatons. Your 1,000-kilogram ship now carries the kinetic energy of 3 Tsar bombers, the largest nuclear weapon ever detonated, and you're still 1% away from light speed. Here's the nightmare. At exactly light speed, Einstein's kinetic energy formula divides by 0. The energy becomes infinite. To accelerate even a single electron to light speed would require all the energy in the universe. Then you'd need more, an infinite amount more. This isn't an engineering problem. No amount of better technology can solve it. The universe fundamentally forbids reaching light speed by making the energy cost infinite. You can keep pouring in energy forever. You'll get closer and closer, adding more nines to your 99.999%. But you will never reach 100%. The Large Hadron Collider demonstrates this brutally. It accelerates protons to 99.99991% light speed. The last tiny sliver, that final 0.000000 entire solar system's worth of energy to gain a single atom's width of additional velocity. But the energy problem goes even deeper than this, because energy isn't the only resource that explodes as you accelerate. The Large Hadron Collider is humanity's attempt to touch light speed, and it's failing in exactly the way Einstein predicted. This machine circles beneath the border of France and Switzerland. 17 miles of superconducting magnets cooled to near absolute zero, the most sophisticated scientific instrument ever built. Its purpose is simple. Accelerate particles as close to light speed as physics allows, then smash them together to see what happens. Protons enter the ring, moving at a decent velocity already. Within minutes, thousands of magnets begin accelerating them. Each lap around the 17-mile circuit adds more energy. The protons move faster. Each pass brings them closer to the ultimate limit. After about 20 minutes of acceleration, the protons reach 99.9% of light speed. They're circling the entire ring 11,000 times per second. At this velocity, time dilation becomes significant. From the proton's perspective, it experiences only a fraction of the time that passes in the laboratory. But from our perspective, it's racing around the ring at nearly light speed. The scientists don't stop. More energy pours in. The magnets keep pushing. The protons accelerate to 99.99%, then 99.999%. Each additional 9 requires exponentially more energy than all previous acceleration combined. Finally, the protons reach their maximum velocity, 99.99999% of light speed. This took enormous amounts of electrical power. The collider consumes as much electricity as a small city. Most of that energy went into this final fraction of a percent. Why can't they go faster? The collider is producing maximum power. The magnets are at peak strength, but the protons simply refuse to accelerate further. Not because the machine is weak, because the proton's relativistic momentum has grown so enormous that even the strongest magnetic fields humanity can generate barely budge them. From the laboratory frame, those protons have a Lorentz factor of about 7,400. Their kinetic energy is 7,400 times their rest mass energy. They carry the momentum of particles thousands of times heavier, even though each proton masses exactly the same as when it started. Scientists can measure everything with exquisite precision. They track individual protons. They measure their energy. They calculate their momentum. Every measurement confirms Einstein's equations perfectly. The relativistic formulas predict exactly how these particles behave at extreme velocities. When two protons collide at this speed, their combined kinetic energy is so immense that it materializes into new particles. Quarks appear. Gluons flash into existence. Sometimes even Higgs bosons, the particles that give other particles mass, emerge from the collision. Pure energy transforms into matter, exactly as Einstein's equation predicts. The collider has been running for over 15 years. Scientists have performed trillions of collisions. They've accelerated countless protons. Not once has any particle exceeded light speed. Not once has any particle even reached light speed. The barrier remains absolute. Other particle accelerators around the world show identical results. Fermilab in the United States, CERN's older machines, the SLAC National Accelerator Laboratory. Every single accelerator that pushes particles to extreme speeds hits the same wall, 99-point-something%. That final fraction remains forever unreachable. These machines don't just prove that nothing can reach light speed, they prove why. The energy requirements explode. The momentum grows without bound. Every prediction of special relativity manifests in measurable, verifiable ways. Physics isn't just theory, it's experimental fact, tested billions of times. If we can't even accelerate a single proton to light speed, despite using our most powerful machines, how could we ever accelerate an entire spaceship? A vessel weighing thousands of tons? The scaling is so ridiculous that it crosses from difficult into impossible. Yet the story gets stranger still, because even if you could somehow ignore all these problems, even if you could magically reach light speed, you would encounter something even more bizarre than energy barriers. You would discover that you're already traveling at light speed right now. You are moving at the speed of light through space-time at this exact moment. This sounds impossible. You're sitting still, reading these words, not moving at 186,000 miles per second, but in the deepest sense, you absolutely are. You're just moving through time instead of space. Einstein's mathematics revealed that space and time aren't separate things. They're dimensions of a single four-dimensional structure called spacetime. 3 dimensions of space: left, right, forward, backward, up, down. 1 dimension of time: past, future. These 4 dimensions combine into one unified fabric. Every object in the universe has a 4-dimensional velocity through space-time. This velocity is always exactly the speed of light. Always. No exceptions. Every particle, every person, every planet moves through space-time at precisely light speed. This is the foundational rule from which all of special relativity flows. Think about directions on Earth's surface. You can move north, you can move east, you can move northeast, combining both directions. But you have limited speed. If you're driving at 60 miles per hour northeast, you might be going 40 miles per hour north and 40 miles per hour east. The 2 components combine to give your total speed. Space-time works similarly, except the dimensions are space and time instead of north and east. You have a total velocity through space-time of exactly light speed. You can divide this velocity between moving through space and moving through time, but the total always equals light speed. When you're sitting still in space, 100% of your space-time velocity goes into moving through time. You're traveling into the future at maximum speed, 1 second per second. That sounds trivial, but it's actually the speed of light through the time dimension. Start moving through space. Walk across the room. Now a tiny fraction of your space-time velocity shifts from the time dimension to space dimensions. You're moving through space at 3 miles per hour. That means you must be moving through time slightly slower. Your clock ticks a tiny bit slower than a stationary clock. The effect is immeasurably small at walking speed, but it's real. Your watch genuinely runs slower by an infinitesimal amount. Not because anything is wrong with your watch, because you're diverting some of your space-time velocity from time into space. Get on an airplane flying at 500 miles per hour. More of your space-time velocity shifts into spatial motion. Your watch now runs measurably slower than ground-based clocks. The difference is tiny, just nanoseconds per flight, but atomic clocks can measure it, and they do. Accelerate to half the speed of light. Now you've diverted half your space-time velocity into spatial motion. That means you're only moving through time at half speed. Your clock ticks at half the rate of a stationary clock. For every hour you experience, 2 hours pass for someone at rest. At 99% light speed, nearly all your spacetime velocity is going into spatial motion. Only a tiny fraction remains for motion through time. Your clock crawls along. Time passes 7 times slower for you than for stationary observers. What happens at exactly light speed? 100% of your spacetime velocity would be directed into spatial motion. 0% would remain for temporal motion. Your clock would stop completely. Time would freeze. No time would pass at all from your perspective. This is why photons don't experience time. A photon emitted from a star 1 million light years away travels for 1 million years from our perspective. But from the photon's perspective, if it had one, no time passes. The photon is created and absorbed in the same instant. It traverses the entire universe in 0 time because it's moving all its space-time velocity through space. Massive objects can never do this. You can approach light speed. You can get 99.9999% of the way there. But you can never quite shift 100% of your space-time velocity into spatial dimensions because that would require infinite energy. There's always some residual motion through time. You can slow your clock dramatically. You can't stop it completely. The universe enforces this rule ruthlessly. Your total space-time velocity is fixed at light speed. You can trade space for time or time for space, but you can never exceed the total. Light speed isn't just the fastest you can move through space. It's the speed you're already moving through space-time right now. This realization leads to even stranger implications. Because if moving faster through space means moving slower through time, then extreme velocities create extreme time distortions. Every mile per hour you gain through space costs you seconds lost through time. This trade-off is the core of special relativity. It's not negotiable. It's not something clever engineering can overcome. It's woven into the mathematical structure of space-time itself. Move faster through space, move slower through time. The exchange rate is determined by the Lorentz factor. At everyday speeds, the trade-off is invisible. Drive at 60 miles per hour, and your clock loses about 2 quadrillionths of a second per hour compared to a stationary clock. This is so small that no clock humans have ever built could measure it directly. For practical purposes, it might as well be 0. The International Space Station orbits at 17,500 miles per hour. Astronauts aboard lose about 7 microseconds per day compared to ground-based clocks. Still tiny, still nearly undetectable without atomic clocks. But now, it's measurable. Scientists can track this difference. GPS. Satellites orbit at 14,000 miles per hour. They're also higher in Earth's gravity field, which creates additional time dilation effects. Combined, GPS satellite clocks run about 38 microseconds per day faster than ground clocks. This matters enormously. Your GPS navigation relies on extremely precise timing. If engineers didn't account for relativistic effects, GPS would accumulate errors of several miles per day. Your smartphone compensates for relativity every time you use navigation. The device receives signals from multiple satellites, calculates distances based on signal travel times, then determines your position. If the satellite clocks weren't corrected for relativistic time dilation, the calculated distances would be wrong. Your position on the map would drift. This isn't theoretical. Early GPS engineers debated whether relativistic corrections were necessary. Some argued the effects were too small to matter. They were wrong. When the system launched, satellites were deliberately programmed with slower clock rates to compensate for predicted relativistic effects. If those corrections were removed, GPS would fail within minutes. So, relativity isn't just abstract physics. It's running in the processor of the device in your pocket right now. Every time you check a map, every time you navigate to a destination, your phone is accounting for the space-time trade-off, pushed to higher velocities, and the trade-off becomes dramatic. At 87% light speed, your Lorentz factor reaches 2. You're trading 1 second of time for every second of normal time. Your clock runs at half speed. Travel for 10 years by your clock and 20 years pass on Earth. At 99.5% light speed, the Lorentz factor hits 10. You age 1 year while Earth ages 10. This is time travel into the future. One-way time travel. You can't go back, but you can leap forward by simply moving fast enough. The trade-off creates a fundamental asymmetry. From your perspective on the spaceship, the journey feels normal. Your clock ticks normally. Your heart beats normally. You age normally. But when you look out the window, Earth appears to be in fast forward. Years blur past in months. Decades compress into years. From Earth's perspective, you're in slow motion. Your clock ticks sluggishly. Your movements are slower. Your aging has nearly stopped. You're becoming a living time capsule, preserved by velocity, while the universe around you ages. This asymmetry is real. It's being tested. Atomic clocks on aircraft show exactly the predicted time differences. Muons created in the upper atmosphere live longer than they should because they're moving at 99.5% light speed. GPS proves it daily. Particle accelerators confirm it billions of times per second. The trade-off is absolute. You cannot move through space without affecting your motion through time. They're locked together, two faces of the same phenomenon. This is why reaching light speed is forbidden. At light speed, you would trade away all motion through time. Your clock would stop. Time would cease to exist from your perspective. But this raises a question that has puzzled people since Einstein first published his theory. If motion affects time, what happens to two people who experience different amounts of motion? Clocks do not keep universal time, and this fact destroys our intuition about reality. Imagine two identical atomic clocks. Perfect synchronization. Each tick represents the same duration. Place them side by side, and they march in lockstep. Now separate them. Leave one on the ground. Put the other in a jet. Fly the jet around the world at typical airliner speeds. When the jet lands, compare the clocks. They disagree. The moving clock has fallen behind by a few hundred nanoseconds. This isn't malfunction. This isn't experimental error. This is time itself, running at different rates for the two clocks. In 1971, physicists Joseph Hafele and Richard Keating did exactly this experiment. They flew cesium atomic clocks on commercial flights around the world. Eastward flights, westward flights, different speeds and directions. When they returned, every single moving clock disagreed with the reference clock left at the Naval Observatory in Washington. The differences matched Einstein's predictions within experimental error. Eastward flights lost time. Westward flights gained time. The exact nanoseconds lost or gained depended on flight speed, direction, and altitude. Special relativity predicted every measurement accurately. This proved something shocking. Time is not absolute. There is no universal clock ticking away in the background. Time is local. Every object has its own proper time. Two objects following different paths through spacetime will age differently. Their clocks will genuinely show different elapsed times. Time dilation grows more extreme as velocity increases. At 10% light speed, the Lorentz factor is 1.005. Time runs at 99.5% normal rate, barely noticeable. At 50% light speed, time runs at 86.6%. Now, it's significant. At 90% light speed, time slows to 43.6% normal rate. You age less than half as fast as someone at rest. Travel for 1 year by your clock, and 2.3 years pass on Earth. The asymmetry becomes dramatic. What causes this? Why does motion through space affect passage through time? The answer lies in the structure of space-time itself. When you move, you're tilting your path through space-time. You're angling more toward space and less toward time. This tilt compresses how much temporal distance you cover per unit of your proper time. Think of walking across a large field. Walk straight north and you cover maximum northward distance. Now, angle northeast. You're still walking at the same speed, but you're covering less northward distance per minute because some of your motion is going eastward. Spacetime works similarly, except the dimensions are space and time instead of north and east. The faster you move through space, the more your path tilts. The more it tilts, the less temporal distance you cover. Your clock ticks slower because you're literally traveling through less time per unit of proper time. It's geometry. The math is ruthless and precise. Muons prove this daily. These particles form when cosmic rays hit the upper atmosphere, about 12 miles up. Muons are unstable. They decay with a half-life of 2.2 microseconds. At light speed, a muon could only travel about 2,000 feet before half of them decay. But muons reach the ground. Detectors at sea level catch them constantly. They've traveled 12 miles, despite only being able to survive for 2,000 feet worth of time. How? Time dilation. The muons are moving at 99.5% light speed. Their internal clocks, it's as proven as gravity, as verified as thermodynamics. Time dilation is real, but this creates an apparent paradox, one that confused physicists for decades after Einstein's paper. One twin boards a spaceship and travels to a distant star at near light speed. The other stays on Earth, and when they reunite, they are no longer the same age. This scenario is called the twin paradox. It's one of the most famous thought experiments in physics, and it reveals something deeply unsettling about time. Start with identical twins, 20 years old, perfect health. One twin, we'll call her Maya, boards an ultra-fast spacecraft capable of 99% light speed. Her sister Arya stays on Earth. Maya accelerates to maximum velocity and heads toward a star 4 light-years away. From Earth's perspective, Maya's journey takes about 4 years to reach the star, 4 more years to return, 8 years total. Arya ages 8 years while waiting. She's now 28 years old. But Maya experiences something different. At 99% light speed, her Lorentz factor is 7.089. Time runs 7 times slower for her. The 8-year journey from Earth's perspective only feels like 1.13 years to Maya. When she returns and steps off the spacecraft, she's 21 years old. Arya is 28. 7 years difference. 2 people who were born on the same day are no longer the same age. Maya has time traveled into the future. She skipped 7 years of Earth's history by moving fast. Here's where people get confused. They ask, isn't motion relative? From Maya's perspective, Earth was the thing moving away at 99% light speed. Shouldn't Arya be the younger one? This is where the word paradox comes from. It seems like both twins should see the other as younger. That's impossible. When they reunite, either Maya is younger or Arya is younger. They can't both be younger than each other. The resolution is subtle but crucial. The situation is not symmetrical. Maya experienced acceleration. Arya did not. Maya had to accelerate to 99% light speed, travel to the star, decelerate, turn around, accelerate back, and decelerate again at Earth. During all these acceleration phases, she was in a non-inertial reference frame. Arya experienced none of this. She stayed in Earth's inertial frame the entire time. She never accelerated. The laws of special relativity work differently for inertial and non-inertial observers. This asymmetry breaks the apparent paradox. Multiple experiments have confirmed this. Not with humans making interstellar journeys, obviously, but with particles and clocks. Muons in storage rings live longer than stationary muons. Atomic clocks on airplanes tick slower than ground clocks. Every test shows the same thing. The twin who travels returns younger. This isn't science fiction. This is confirmed reality. If we built a spacecraft capable of 99% light speed and sent someone on a round trip to a nearby star, they genuinely would return younger than their twin who stayed home. The time difference would be measurable, real, permanent. The twin paradox demonstrates the ultimate implication of time dilation. Travel fast enough, and you become a time traveler. One way only, always into the future, never to the past. You can't undo it. You can't reverse it. Maya can never get those 7 years back. She's permanently 7 years younger than Arya now. For space travel, this creates both opportunity and tragedy. The opportunity: you could journey to distant stars and return while relatively little time passes for you. The tragedy: everyone you left behind will age faster. Your children could be elderly when you return from a journey that felt like mere months to you. Science fiction has explored this thoroughly. The Forever War by Joe Haldeman, Planet of the Apes. Countless stories about time dilation's emotional consequences. The physics makes it unavoidable. Travel at relativistic speeds, and you become unstuck in time from everyone else. But we haven't even discussed the strangest verification of time dilation, one that happens 20,000 miles above your head right now. GPS satellites are proving Einstein right 24 hours a day, and they have to, or your navigation would fail catastrophically. 24 satellites orbit Earth at 12,430 miles altitude. They circle the planet twice daily. Each satellite carries atomic clocks accurate to billionths of a second. These clocks are fundamental to how GPS works. Your phone receives signals from multiple satellites. Each signal includes the exact time it was transmitted. Your phone calculates how long each signal took to reach you based on travel time at light speed. With distances from 4 or more satellites, it triangulates your exact position on Earth's surface. This requires extraordinary timing precision. Light travels 1 foot in about 1 nanosecond. An error of just 100 nanoseconds in clock synchronization translates to 100 feet of position error. Modern GPS aims for accuracy within 10 feet. That means clock errors must stay below 10 nanoseconds. Here's the problem. Special relativity predicts that GPS satellite clocks should run slower than ground clocks because the satellites are moving at 8,750 miles per hour. Time dilation should cause them to lose about 7 microseconds per day. But general relativity also matters. The satellites orbit in weaker gravity than Earth's surface. General relativity predicts that clocks run faster in weaker gravitational fields. This effect should cause satellite clocks to gain about 45 microseconds per day. Net result: GPS satellite clocks should gain about 38 microseconds per day compared to ground clocks. 7 lost from velocity, 45 gained from altitude, 38 total. Engineers faced a choice when designing GPS: account for relativity or ignore it. Some argued the effects were too small to matter. Others insisted relativistic corrections were essential. After much debate, they decided to include the corrections. Here's what they did. GPS satellite clocks are deliberately programmed to tick slightly slower than ground clocks before launch. The rate is adjusted by exactly the amount relativity predicts. When the satellites reach orbit, relativistic effects speed their clocks up to the correct rate. The clocks then stay synchronized with ground time. What if engineers had ignored relativity? The satellite clocks would drift. 38 microseconds per day doesn't sound like much. But at light speed, 38 microseconds equals 7.1 miles. After 1 day, GPS would have position errors of 7 miles. After a week, 50 miles. After a month, over 200 miles. The system would be useless. This isn't theoretical. In the early days of GPS, engineers ran tests with and without relativistic corrections. Without corrections, the system failed exactly as Einstein's equations predicted. With corrections, GPS worked perfectly. Relativity isn't optional, it's essential. Every GPS device in the world depends on this. Your car navigation, your phone's maps, aircraft navigation systems, missile guidance, ship positioning, survey equipment. All of it requires relativistic time corrections. Without Einstein's equations, modern navigation would be impossible. GPS satellites have been operating since 1978. Billions of position calculations daily, trillions over the decades. Every single one confirms special and general relativity. The time dilation is universal. Even the International Space Station experiences time dilation. At 250 miles altitude, orbiting at 17,500 miles per hour, astronauts age about 7 microseconds less per day than people on Earth. Over 6 months in space, they return about a millisecond younger than if they'd stayed on the ground. The effects are tiny at these velocities, but they're real, measurable, confirmed. Every spacecraft, every satellite, every high-speed particle, they all experience time dilation, exactly as special relativity predicts. But GPS satellites aren't the only proof falling from the sky. There's an even more dramatic demonstration happening right now in the upper atmosphere. Cosmic rays are smashing into the atmosphere 12 miles above your head, creating particles that shouldn't exist long enough to reach the ground, yet they do. Cosmic rays are high-energy particles from space, mostly protons. They slam into nitrogen and oxygen molecules in the upper atmosphere at nearly light speed. These collisions create showers of new particles, among them muons. Muons are like heavy electrons, same electric charge, about 200 times more mass, fundamentally unstable. A muon at rest will decay into an electron and 2 neutrinos with a half-life of 2.2 microseconds. That's 2.2 millionths of a second. Blink and a muon is long gone. Do the math. Light travels at 186,000 miles per second. In 2.2 microseconds, even traveling at light speed, a muon could only cover about 2,000 feet before half of them decay. After another 2 microseconds, half of the remaining muons decay. After 10 microseconds, over 97% have disappeared. Cosmic ray collisions happen about 12 miles up. That's 63,360 feet. If muons travel at light speed but decay after covering 2,000 feet, almost none should reach the ground. You'd need to go through 31 half-lives to travel 12 miles. After 31 half-lives, less than 1 in 2 billion muons survive. Place a muon detector at sea level. According to classical physics, you should barely detect any muons, maybe a handful per hour on a sensitive detector. The vast majority should decay long before reaching the ground. Run the experiment. The detector clicks constantly. Hundreds of muons per hour. Thousands. Far, far more than classical physics predicts. Muons are reaching the ground despite theoretically not having enough time to make the journey. This puzzled physicists before relativity. The numbers didn't add up. Muons were surviving impossible journeys. Something was allowing them to travel distances they shouldn't be able to reach. Einstein's time dilation solves it perfectly. Muons from cosmic ray collisions are moving at about 99.5% light speed. At this velocity, the Lorentz factor is roughly 10. From our reference frame, the muons' internal clocks run 10 times slower than normal. Their 2.2 microsecond half-life stretches to 22 microseconds from our perspective. At light speed, 22 microseconds allows traveling about 13,000 feet instead of 2,000. Still not enough to cover 12 miles. But here's the key. From the muons' reference frame, something different happens. Length contraction. The 12-mile distance shrinks to 1.2 miles. The muon only needs to survive long enough to travel 1.2 miles, which it can easily do in 2.2 microseconds. Both perspectives give the same result. From our frame, the muon lives longer. From the muon's frame, the distance is shorter. Either way, muons reach the ground in numbers that match relativistic predictions perfectly. Scientists have measured this extensively. Detectors at various altitudes count muon rates. Mount Washington in New Hampshire, Pikes Peak in Colorado, sea level detectors worldwide. The altitude distribution of muons matches Einstein's equations precisely. More muons at higher altitudes, fewer at sea level. The decay rate follows the relativistic time dilation curve exactly. This isn't a one-time experiment. This is continuous verification. Every second of every day, thousands of muons are demonstrating time dilation. They're natural particle accelerators, created by the universe, proving relativity automatically. You can build your own muon detector. Several universities offer plans. Some high school students have built working detectors in their garages. Put one at sea level, and you'll count muons all day and night. Those muons are direct proof that time dilation is real. Particle physics labs exploit this. When they accelerate muons in storage rings, the muons live longer than they would at rest. The decay rate depends exactly on velocity. 99% light speed. 99.9%. The higher the velocity, the longer the muons survive, matching relativistic predictions every time. Muons aren't special. All unstable particles behave this way. Pions, kaons, tau particles. Every particle with a finite lifetime lives longer when moving fast. Time dilation applies universally. It's not about muons specifically. It's about time itself working differently for objects in motion. But all these examples involve tiny particles or atomic clocks showing nanosecond differences. Is there any way to see relativistic effects on larger scales? Any way the universe demonstrates these principles in ways humans can more directly grasp? For thousands of years, humanity wondered whether light traveled instantly or took time to cross distances, and the answer would eventually reveal the universe's deepest speed limit. Ancient Greeks debated light's nature. Empedocles argued light takes time to travel. Aristotle disagreed, claiming light moved instantly. No experiment could settle the debate. Light seemed too fast to measure. In 1638, Galileo tried. He and an assistant stood on hilltops several miles apart at night. Each held a shuttered lantern. Galileo would uncover his lantern. The moment his assistant saw the flash, he'd uncover his own. Galileo would measure how long the return flash took. The experiment failed completely. Human reaction time is about 200 milliseconds. Light crosses several miles in mere microseconds. Galileo couldn't possibly detect such a brief delay. He concluded only that light was extremely fast, perhaps instantaneous. The breakthrough came from astronomy. In 1676, Danish astronomer Ole Rømer was studying Jupiter's moon Io. Io orbits Jupiter every 1.769 days, passing into Jupiter's shadow each orbit. These eclipses should happen at predictable intervals. Rømer noticed something strange. When Earth moved away from Jupiter in its orbit, Io's eclipses arrived late. When Earth approached Jupiter, eclipses arrived early. The timing errors accumulated to more than 10 minutes over several months. Rømer realized light must have a finite speed. When Earth was farther from Jupiter, light had to travel a greater distance to reach Earth. The accumulated delay revealed how much additional distance light traveled. From this, Rømer calculated light speed at about 140,000 miles per second. The true value is 186,000 miles per second. Rømer's estimate was low because estimates of Earth's orbital size were inaccurate in 1676, but he proved the critical point. Light has a measurable, finite speed. In 1849, French physicist Hippolyte Fizeau made the first Earth-based measurement. He used a rapidly spinning toothed wheel. A light beam passed through a gap between teeth, traveled 5 miles to a mirror, reflected back. If the wheel rotated at just the right speed, the return beam would hit a tooth and be blocked. By measuring the rotation speed, Fizeau calculated light's velocity. His answer, 195,000 miles per second. Close. Getting better. Over the next decades, increasingly sophisticated experiments refined the measurement. By the late 1800s, scientists knew light speed to within 1% of the modern value. These measurements revealed something peculiar. Light's speed appeared to be constant. Different experimenters, different methods, different conditions. Everyone measured essentially the same value. This seemed strange because speeds usually depend on reference frame. In 1887, Albert Michelson and Edward Morley performed a crucial experiment. They split a light beam, sent the components in perpendicular directions, then recombined them. As Earth orbited the Sun, the apparatus orientation changed relative to Earth's motion. Classical physics predicted the light's travel time should vary depending on whether it moved with or against Earth's motion. The The experiment detected no variation. Light speed was the same in all directions, regardless of Earth's motion through space. This made no sense under classical physics. How could light speed be independent of the observer's motion? Einstein resolved this in 1905 with special relativity. He made light's constant speed a fundamental postulate. The speed of light isn't constant because there's something special about light. It's constant because space-time itself has this property. Light speed is the conversion factor between space and time. It's built into the geometry of the universe. Modern measurements give light's vacuum speed as exactly 186,282.397 miles per second. This value is now defined, not measured. The meter itself is defined as the distance light travels in 1,299,792,458 of a second. Humanity spent millennia discovering light speed. Once we knew it, we discovered it was the universal speed limit. Nothing can go faster. The measurement that began with Galileo's failed lantern experiment ended up revealing one of the universe's most fundamental laws. But why is light speed constant? What makes this particular velocity so special? Light speed is not just the fastest anything can go, it's the exchange rate between space and time, and this makes it invariant across the universe. In everyday life, speeds add. You're on a train moving 50 miles per hour. Walk forward at 3 miles per hour. From the ground, you're moving at 53 miles per hour. Simple addition. This works fine at normal velocities, but it breaks down near light speed. Imagine a spacecraft moving at 90% light speed. You shine a flashlight forward from inside the ship. Classical physics says the light should move at 1.9 times light speed from an outside observer's perspective. Light speed plus ship's speed. This never happens. The outside observer measures the light moving at exactly light speed. Always. The light doesn't travel faster just because it was emitted from a moving source. Light speed is absolute. It doesn't depend on the motion of the source or observer. This seems impossible. How can light move at the same speed for both the person on the ship and the stationary observer? The ship is moving at 90% light speed relative to the observer. Shouldn't their measurements differ? They do differ, but not in the light speed. They differ in time and space themselves. The person on the ship experiences time slower than the stationary observer. Distances appear contracted from the ship's perspective. These distortions perfectly compensate. Both observers measure identical light speed despite their relative motion. Einstein's mathematics shows this must happen. If light speed is constant, then space and time must be flexible. There's no other possibility. The universe can't simultaneously have constant light speed and absolute time. Something has to give. Time and space give. Why is light speed specifically the constant that never changes? Because it's not really about light at all. It's about the structure of space-time itself. Light speed is the maximum rate at which cause can become effect. It's the speed at which causality propagates through the universe. Think of it as the universe's frame rate. Reality updates at a certain maximum speed. Information can't travel faster than this speed because the universe can't process events faster than this. Light moves at this speed because photons are massless. Anything massless automatically moves at the universal update rate. Massive objects move slower because they can't keep up with the maximum update speed. The more mass, the more inertia. The slower the maximum speed. Only massless particles reach the ultimate limit. Light, gluons, gravitational waves, all massless, all traveling at exactly c. The value 186,000 miles per second isn't arbitrary. It's a consequence of how electromagnetic forces work. Maxwell's equations from the 1860s predicted electromagnetic waves would travel at a specific speed, calculable from the properties of electric and magnetic fields. That speed turned out to match the measured speed of light. Light speed emerges from deeper physics. It's not a random number the universe picked. It's a consequence of the electromagnetic force's properties, which themselves derive from quantum field theory, which derives from even deeper principles we're still uncovering. But regardless of why this particular value, the fact that it's constant has profound implications. Constant light speed forces time dilation and length contraction. These aren't separate phenomena. They're necessary consequences of light speed invariance. Every attempt to measure light speed, regardless of the observer's motion, yields the same value: moving toward a light source, moving away, standing still, spinning, accelerating. Doesn't matter. Light always approaches at 186,000 miles per second. This constancy is perhaps the most well-verified fact in physics. The constancy of light speed is what makes GPS work. It's why particle accelerators behave as they do. It's why time dilation and length contraction occur. It's the foundation of modern physics. Change this one property, and the entire universe would work differently. Light speed's constancy isn't a speed limit in the sense of a rule you could break. It's more like the exchange rate between two currencies. You can't make the exchange rate different by wanting it badly. It's a property of the system itself. Light speed is the exchange rate between space and time. That rate is fixed by the universe's geometry. This leads to something that confused people for decades, because if light speed is constant, and motion through space trades off with motion through time, what happens to your mass as you accelerate? Does it increase? The answer surprised physicists. Your mass does not increase as you approach light speed, and understanding this corrects one of physics' most common misunderstandings. For decades, physics teachers told students that mass increases with velocity. Textbooks called it relativistic mass. The idea seemed intuitive. As you go faster, you become harder to accelerate. This looks like gaining mass. If mass is increasing, that explains why reaching light speed is impossible. Your mass would become infinite. This explanation is wrong, or at least misleading. Modern physics doesn't use relativistic mass anymore, because mass doesn't actually increase. Something else does. Your rest mass is invariant. A 1,000 kilogram spacecraft has 1,000 kilograms of rest mass, whether it's parked or flying at 99% light speed. Put it on a scale when it's stationary, and it reads 1,000 kilograms. The mass literally does not change. What changes is inertia, resistance to acceleration. At 99% light speed, the spacecraft resists acceleration as if it had 7,000 kilograms instead of 1,000. But this isn't because it gained 6,000 kilograms of mass. It's because relativistic momentum grows with the Lorentz factor. The distinction matters. Mass is a source of gravitational fields. If a spacecraft actually gained mass while moving, its gravitational pull would increase. A fast-moving ship would have stronger gravity than a stationary one. This doesn't happen. The ship's gravitational field doesn't change with velocity. A 1,000 kilogram spacecraft generates the same gravitational pull whether parked or moving at near light speed. Its gravity pulls other objects with force corresponding to 1,000 kilograms, not 7,000. The mass hasn't increased, only the inertia has. Why did physicists ever talk about relativistic mass? Because it was a convenient teaching shortcut. Multiply rest mass by the Lorentz factor, and you get a quantity that works in many relativistic equations. It makes the formulas look more familiar to students learning relativity for the first time. But relativistic mass creates more confusion than it solves. Students think mass genuinely increases. They incorrectly predict stronger gravity for fast-moving objects. They misunderstand what's physically changing. Modern physics education has largely abandoned the concept. What actually increases is the momentum-energy relationship. Your total energy grows with the Lorentz factor. Your momentum grows with the Lorentz factor, but your rest mass stays constant. The growth in energy and momentum creates the increased resistance to acceleration without requiring actual mass increase. Einstein's famous equation is usually written E equals mc squared, but this is only valid for objects at rest. The full equation is E squared equals P squared C squared plus M squared C to the fourth. E is total energy. P is momentum. M is rest mass. C is light speed. For an object at rest, momentum is 0. The equation simplifies to E equals mc squared. But for a moving object, both terms contribute. The momentum term grows with velocity. At high speeds, it dominates. Total energy explodes toward infinity, even though rest mass stays constant. This is why acceleration becomes impossible at light speed. Not because mass becomes infinite, because the momentum term becomes infinite. The energy required to further increase momentum approaches infinity. You can't add infinite energy. The acceleration stops. Particle accelerators prove this constantly. They accelerate protons to within a fraction of a percent of light speed. The proton's rest mass never changes. Their inertia increases enormously. Their resistance to further acceleration grows with the Lorentz factor, but weigh them and they'd still show their original rest mass. The misunderstanding about relativistic mass probably caused confusion for thousands of students. Some went on believing mass genuinely increases. They might have asked questions like whether gravitational effects increase for fast spacecraft. The answer is no, because mass is invariant. Physics has corrected this. Modern textbooks teach rest mass as invariant and explain time dilation and length contraction as the true relativistic effects. This gives a clearer picture of what's actually happening physically. Your rest mass is a property of matter itself. It doesn't depend on motion. It's the m in E equals mc squared. It's the quantity that determines gravitational pull. It never changes regardless of velocity. What changes is how that mass responds to forces, how difficult it is to accelerate further, how much momentum and energy it carries. The misconception arose from well-meaning attempts to simplify relativity, but sometimes simplifications create more problems than they solve. The truth is actually cleaner. Your mass stays constant. Spacetime warps around you as you move, and the structure of reality makes infinite acceleration impossible. But if mass stays constant, yet acceleration becomes impossible, where exactly does all that energy go? Let's try to accelerate a spacecraft to 99% light speed and watch the numbers become nightmares. Start with a modest vessel, 10,000 kilograms, about the mass of a large van, not a massive starship, just a small crew capsule with minimal supplies. We want to push this craft to 99% of light speed. How much energy do we need? Einstein's relativistic kinetic energy formula gives the answer. At 99% light speed, the Lorentz factor is 7.089. Plug in the numbers, and you get 4.5 times 10 to the 20th power joules. That's 450 billion joules. What does this number mean in practical terms? A ton of TNT releases about 4 billion joules when detonated. Our spacecraft needs the equivalent of 112 million tons of TNT. That's over 2,000 times the energy of the largest nuclear weapon ever built. The Tsar bomber released 50 megatons. We need 2,250 Tsar bombas worth of energy just to accelerate one small spacecraft. The United States uses about 100 quadrillion joules of energy per year. Total. Every power plant, every vehicle, every device. Our spacecraft needs about 0.5% of America's annual energy consumption. For a single launch, for one small vessel, carrying maybe 3 people, scale up to 99.9% light speed. The energy requirement multiplies by 3. Now you need 1,400 billion joules. That's 1.4% of America's yearly energy use. For each additional 9, you add to the decimal of fuel energy into kinetic energy. Ion drives manage 40% on a good day. Factor in realistic efficiency, and the numbers get far worse. But even with perfect efficiency, where does this energy come from? You can't carry it with you in batteries. The best battery technology stores about 1 million joules per kilogram. To carry 4.5 times 10 to the 20th joules, you'd need 450 trillion kilograms of batteries. That's 45 million times more massive than the spacecraft itself. Solar panels won't work. At Earth's orbit, sunlight delivers about 1,400 watts per square meter. To collect 4.5 times 10 to the 20th joules in a reasonable time frame, you'd need solar arrays, larger than continents, running for years. Nuclear reactors. A large nuclear power plant generates about 1 billion watts. Running continuously for 1 year produces about 3.1 times 10 to the 16th joules. You'd need 14,000 power plants running for 1 year to accumulate enough energy for a single launch. Earth has about 450 nuclear reactors total. The International Space Station took 13 years and over $100 billion to build. It masses 420,000 kilograms and orbits at 17,000 miles per hour. Accelerating it to 99% light speed would require about 19 million times more energy than it took to launch it to orbit. These numbers aren't just big, they're civilization scale. Accelerating spacecraft to relativistic speeds requires energy resources beyond what humanity currently produces, not by a little, by factors of thousands or millions. We're not talking about better rockets. We're talking about energy production that exceeds our entire planetary infrastructure. And we haven't even addressed the hardest problem yet, because spacecraft can't just accumulate energy magically. They have to carry fuel. And the fuel problem makes the energy problem look trivial. Rockets must carry their own fuel, and this creates a catastrophic mathematical trap that destroys any hope of relativistic travel. The rocket equation governs all spacecraft. It's called the Tsiolkovsky equation, after the Russian scientist who derived it in 1897. The formula relates your final velocity to your initial mass, final mass, and exhaust velocity. More fuel means higher speed, but you have to carry that fuel, which makes you heavier, which requires more fuel. This creates exponential growth. To go twice as fast, you don't need twice as much fuel. You need exponentially more. The equation contains a natural logarithm. Small changes in velocity require large changes in fuel mass ratio. For chemical rockets, exhaust velocity tops out around 10,000 miles per hour. To reach orbital velocity of 17,000 miles per hour, you need about 9 kilograms of fuel for every kilogram of payload. The rocket is 90% fuel by mass. That's manageable. We do it regularly. Now aim for 1% of light speed, about 6,700,000 miles per hour. With chemical rockets, you'd need a fuel-to-payload ratio so large it exceeds the mass of the observable universe. Chemical propulsion is completely useless for relativistic speeds. Ion drives do better. Exhaust velocities reach 120,000 miles per hour, much more efficient. For 1% light speed, you need about 60 kilograms of fuel per kilogram of payload. That's theoretically achievable, difficult but possible. Push to 10% light speed. Ion drives now require about 6 million kilograms of fuel per kilogram of payload. Your 1,000 kilogram spacecraft needs 6 billion kilograms of fuel. That's 6 million tons. The entire International Space Station masses 420 tons. Your fuel alone masses 14,000 times more than the ISS. At 50% light speed, even with perfect matter-antimatter annihilation providing maximum theoretical efficiency, you need 1.7 kilograms of fuel for every kilogram you want to deliver. So, a 1,000 kilogram spacecraft requires 1,700 kilograms of fuel. Total launch mass is 2,700 kilograms. Difficult, but theoretically within physics. But you also need to slow down at your destination. Deceleration requires the same amount of fuel as acceleration. Now, you need to carry deceleration fuel during acceleration. The fuel mass ratio squares. Instead of 1.7, you need about 4.6 kilograms of fuel per payload kilogram. Still barely manageable. Jump to 90% light speed. With perfect matter-antimatter annihilation, you need 6.6 kilograms of fuel per kilogram of payload for one-way travel. For a round trip with deceleration and acceleration back home, you need 43 kilograms of fuel per kilogram of payload. Your 1,000 kilogram spacecraft requires 43,000 kilograms of fuel. At 99% light speed, the numbers explode. 14 kilograms of perfect fuel per kilogram of payload one way. 200 kilograms for a round trip with stops. Your 1,000 kilogram spacecraft needs 200,000 kilograms of antimatter fuel. Where exactly do you get 200 tons of antimatter? Humanity has produced about 20 nanograms of antimatter total throughout history. That's 20 billionths of a gram. We need 200,000 kilograms. We're short by a factor of 10 trillion. At current production rates, we'd need trillions of years to accumulate enough antimatter for one ship. Even if we could produce the antimatter, storing it is impossible with current technology. Antimatter annihilates instantly on contact with normal matter. It must be confined in magnetic traps. The largest antimatter trap ever built holds about 1 billionth of a gram. Scaling to tons is beyond any conceivable technology. The fuel problem gets worse at higher speeds. At 99.9% light speed, you need about 90% efficiency is extraordinarily difficult. Real efficiency would multiply these fuel requirements by additional factors. The rocket equation creates an insurmountable barrier. To go faster, you need more fuel. More fuel makes you heavier. Being heavier requires even more fuel. The spiral never ends. At relativistic speeds, the fuel mass grows faster than the benefit you gain from carrying it. But what if we had access to the most efficient fuel theoretically possible? What if matter-antimatter reactions were practical? Antimatter is the most energy-dense fuel that can possibly exist, and even this ultimate fuel isn't enough to make light-speed travel practical. When matter meets antimatter, both annihilate completely. Every atom converts to pure energy, 100% mass to energy conversion. Einstein's E equals mc squared, operating at maximum efficiency. 1 kilogram of matter plus 1 kilogram of antimatter releases 1.8 times 10 to the 17th joules. That's 43 megatons of TNT equivalent. No other fuel comes close. Chemical reactions release a few million joules per kilogram. Nuclear fission releases about 80 trillion joules per kilogram. Nuclear fusion releases about 300 trillion joules per kilogram. Matter-antimatter annihilation releases 90 quadrillion joules per kilogram. It's 10 million times better than chemical fuel, over 1 million times better than nuclear fission. This is the absolute ceiling. No fuel can be more energy-dense than total mass conversion. Antimatter represents the theoretical maximum. If antimatter doesn't solve the relativistic rocket problem, nothing will. But as we just calculated, even antimatter isn't enough. At 99% light speed, you still need 14 times your payload mass in fuel. At 99.9%, 56 times. The ratios remain impossibly large, even with perfect fuel. Antimatter has additional nightmarish problems beyond just quantity. Creating it requires enormous energy. CERN's antimatter factory produces about 10 million antiprotons per minute. That sounds impressive, until you realize it takes 100 billion antiprotons to make 1 nanogram. Current production rates yield maybe 20 nanograms per year. Creating antimatter is energy negative. You put in far more energy than you get back from annihilation. Producing 1 gram requires about 25 trillion kilowatt hours of electricity. That's more than the annual electricity production of several countries. The energy investment to create antimatter fuel exceeds the energy you extract from using it. Storage is nearly impossible. Antimatter annihilates on contact with any normal matter. It must be suspended in perfect vacuum using magnetic fields. The traps are fragile. Power loss means immediate catastrophic annihilation. The largest antimatter storage ever achieved held 1 trillionth of a gram for about 17 minutes. Scaling to tons is pure fantasy. You'd need magnetic containment systems so powerful and reliable they never fail even briefly. A single glitch and your entire fuel load detonates with force exceeding all nuclear weapons ever built combined. Your spacecraft would vaporize, along with everything nearby. Even if you solved production and storage, using antimatter as rocket fuel presents engineering nightmares. The annihilation produces gamma rays. These high-energy photons don't provide thrust directly. You need to convert gamma radiation into charged particles that magnetic nozzles can direct. Efficiency drops. Heat becomes a massive problem. Perfect matter-antimatter. Annihilation produces temperatures beyond anything that can exist in normal matter. Billions of degrees. Nothing can withstand this. Your reaction chamber would vaporize instantly. You need plasma containment, magnetic deflection, and cooling systems that push the absolute limits of physics. And after solving all these problems, you still can't reach light speed. You can barely reach 99%. The fuel ratios remain stubbornly enormous. Perfect fuel only shifts the impossible a bit closer to extremely difficult. It doesn't make light speed achievable. Some physicists have proposed matter-antimatter beam propulsion. Generate antimatter at a space station. Beam it to the spacecraft as it accelerates. This avoids carrying fuel. But now you need to beam antimatter across billions of miles with perfect precision while your target moves at near light speed. The targeting and timing challenges are staggering. Antimatter represents our best theoretical fuel. If it's not sufficient, then rockets, as we understand them, simply cannot reach light speed. The physics won't allow it. The energy density ceiling has been reached. There's nothing better. But energy and fuel aren't the only problems with light speed travel. Something far stranger happens to reality itself as you accelerate. Something that would make the journey profoundly disturbing. At exactly light speed, time ceases to exist, and this reveals why nothing with mass can ever reach this ultimate velocity. Imagine a photon born inside the sun's core. Nuclear fusion creates it deep within the solar furnace. It begins a journey to the sun's surface. The core is incredibly dense. The photon collides with atoms, gets absorbed, re-emitted, bounces randomly. The journey to the surface takes thousands of years from our perspective, but from the photon's perspective, no time passes. Zero. The photon is created and absorbed in the same instant. The entire journey happens in precisely zero time. It experiences no duration whatsoever. This is what traveling at light speed means. Your clock stops, not slows. Stops completely. If you could somehow accelerate to light speed, time would freeze for you. The beginning and end of your journey would be simultaneous. You'd arrive at your destination in the same instant you departed. The math shows this brutally. Time dilation factor equals 1 divided by the square root of 1 minus velocity squared over light speed squared. At exactly light speed, you're dividing 1 by 0. The result is undefined, infinite. Mathematics breaks down. The concept of duration ceases to exist. Think about what this means. You cannot experience traveling at light speed because experience requires time. Thoughts require time. Perception requires time. All of these would stop. You wouldn't experience an instant journey. You wouldn't experience anything. Experience itself would be impossible. Your journey across the galaxy would take thousands of years from Earth's perspective. From your perspective, it would take 0 time. Not a small amount of time. Not a brief instant. Literally 0. The concepts of before and after would not exist for you. This is fundamentally different from normal time dilation. At 99% light speed, time runs slowly, but it still runs. You still experience duration. Thoughts still progress. You age, just slowly. But at exactly light speed, the progression of time halts completely. Photons exist in an eternal frozen moment. Every photon that has ever been created experiences its entire existence as a single, timeless instant. From a photon's perspective, the universe begins and ends simultaneously. It witnesses all of time collapsed into a single point. This is physically impossible for anything with mass. You cannot exist without time passing. Your atoms vibrate. Electrons orbit nuclei. These are processes that require time. Without time, matter cannot function. The structure of atoms depends on temporal progression. Your neurons fire at specific rates. Electrical signals propagate through nerves at finite speeds. Chemical reactions proceed through intermediate states. All of this requires time to flow. Freeze time and all biological function stops, not pauses, stops. The difference is crucial. Consciousness especially requires time. Thinking is a process. Information flows through neural networks. Patterns evolve. Memory formation depends on before and after. Freeze time and consciousness becomes impossible. You couldn't think. You couldn't be aware. You wouldn't experience the frozen moment. Even if you could somehow exist at light speed, you couldn't slow down. Deceleration requires experiencing time. You fire retro rockets. The fuel burns. The thrust builds. The velocity decreases. Each of these is a temporal process. Without time, change cannot occur. You'd be locked at light speed forever, experiencing nothing, unchanging for eternity. This is why light speed is forbidden for massive objects, not just because of energy requirements, not just because of fuel needs, because existence itself requires time, and time stops at light speed. The universe protects causality by making light speed physically unreachable. Approach 99.999% and time nearly stops. Approach 99.99999% and it crawls at a millionth of normal rate. But that last infinitesimal fraction, the gap between almost light speed and exactly light speed, is infinitely wide in terms of what must change. The Lorentz factor approaches infinity. Time dilation approaches infinity. Your clock's tick rate approaches zero, but zero itself is unreachable. You can get arbitrarily close. You can never arrive. Mathematics and physics both forbid it. At light speed, the duration of any journey becomes undefined. The concept breaks. You cannot meaningfully discuss how long something takes when time has stopped. The question itself is nonsensical, like asking what's north of the North Pole. But time isn't the only thing that breaks down. Space itself warps in equally bizarre ways. Space shrinks in the direction of motion, and at extreme velocities, the entire universe appears compressed to paper-thin dimensions. Einstein's special relativity predicts something strange happens to distance itself. As you accelerate, lengths contract in your direction of motion, not from your perspective, from the perspective of stationary observers. To them, your spacecraft physically shrinks. At 10% light speed, the contraction is tiny. Your 10-meter spacecraft appears 9.95 meters long to stationary observers, barely noticeable. At 50% light speed, it appears 8.66 meters. Now it's measurable. Your ship has compressed by over a meter. At 90% light speed, the spacecraft appears 4.36 meters long, less than half its rest length. The ship hasn't been crushed. Nothing has deformed it. Space itself has contracted. From the stationary observer's view, your ship is physically shorter in the direction of motion. From your perspective, inside the spacecraft, nothing seems wrong. You measure the interior dimensions, and everything appears normal, 10 meters from front to back. But when you look out the window, the universe appears compressed. Stars ahead, bunched together. Distances shrink. The space between objects decreases. At 99% light speed, your 10-meter ship appears 1.41 meters long to stationary observers. It's been compressed to 14% of its rest length. But from inside, you measure 10 meters. The disagreement is real. Both measurements are valid in their respective reference frames. This isn't optical illusion. This isn't measurement error. Length contraction is as real as time dilation. Space genuinely compresses in the direction of motion. Experiments with particle beams confirm this. High-velocity particles traverse distances their lifetimes shouldn't allow because the distances contract from their reference frame, pushed to 99.9% light speed. Your ship appears 4.47 centimeters long. That's less than 2 inches. A 10-meter spacecraft compressed to pocket-sized dimensions. From inside, you still measure 10 meters. The universe outside appears squashed dramatically. Distances in front of you shrink to tiny fractions. At 99.99% light speed, objects in the direction of motion appear compressed by a factor of 70. A galaxy spanning 100,000 light-years appears only 1,400 light-years across. The entire structure pancakes flat in the direction of travel. The Lorentz contraction equation matches the time dilation equation. They're two sides of the same phenomenon. As time slows by a factor, lengths contract by the same factor. The Lorentz factor governs both. They're intimately connected through the geometry of spacetime. This is how muons reach Earth's surface. From our perspective, the muons live longer because of time dilation. From the muon's perspective, the distance to the ground shrinks because of length contraction. Both viewpoints give the same result. Muons survive the journey. Length contraction has bizarre implications. As you approach light speed, the universe ahead contracts more and more. At extreme velocities, billions of light-years of space compress to manageable distances from your perspective. You could cross the galaxy in subjective time of months or years, because the galaxy appears only thousands of miles wide to you. But here's the catch. You're still traveling billions of light-years from Earth's perspective. Billions of years pass on Earth during your journey. You've time-traveled into the future by enormous amounts. When you return, everyone you knew is long dead. Civilizations have risen and fallen. The time dilation and length contraction are two perspectives on the same relativistic effect. At exactly light speed, lengths contract to zero in the direction of motion. The entire universe compresses to an infinitely thin sheet perpendicular to your motion. Distance ceases to exist. Every point in the universe becomes equidistant. You'd be everywhere and nowhere simultaneously. This is another reason light speed is forbidden. Distance is fundamental to how reality works. Objects are separated. Events occur at different locations. Compress all distance to zero, and spatial relationships become meaningless. Where would you even be? Particle accelerators observe length contraction routinely. Protons traveling near light speed experience contracted distances. The 17-mile ring appears shorter from their reference frame. This shortening exactly matches the time dilation observed in their decay rates. The physics is consistent. The math works perfectly. Length contraction isn't about objects being squeezed. It's about space itself having different properties depending on relative motion. Space is not absolute. It's observer-dependent. Just like time, the unified space-time structure means both must vary together. But time stopping and space vanishing aren't the worst consequences of light-speed travel. Something far more dangerous emerges. Something that threatens the logical consistency of reality itself. Travel faster than light, and you could theoretically kill your grandfather before your father was born, destroying the logical foundation of the universe. Causality is the principle that effects follow causes. You flip a switch, then the light turns on. The cause comes first, the effect comes after. This seems obvious. This seems unbreakable. Special relativity reveals it's intimately connected to the speed of light. Information cannot travel faster than light. This isn't just a technical limitation. It's fundamental to causality itself. If information could travel faster than light, the order of events would become observer-dependent. Different observers would disagree on what happened first. Imagine a spaceship traveling faster than light. From Earth's perspective, it departs Monday and arrives Tuesday. Simple cause and effect. But from certain other reference frames moving relative to Earth, the arrival happens before the departure. Effect precedes cause. The ship arrives Tuesday, then leaves Monday. This violates causality. Effects cannot precede causes. That would mean results happen before their causes exist. It's logically incoherent. The universe cannot function this way. Physics would become contradictory. Special relativity shows that faster-than-light travel is equivalent to time travel into the past. If you could send a signal faster than light, you could arrange it so the signal arrives before you sent it. You'd receive a message before you transmitted it. The information would travel backward in time. Combine this with relativity of simultaneity and paradoxes emerge. Send a faster-than-light message to a moving spacecraft. They receive it. They send a faster-than-light reply. Under certain conditions, their reply arrives before your original message. You receive the response before sending the question. The grandfather paradox is the classic example. Travel back in time. Kill your grandfather before your father was born. Now your father never exists. You were never born. But if you were never born, you couldn't have traveled back to kill your grandfather. He survives. Your father is born. You exist. You travel back. The loop is logically impossible. Faster-than-light travel creates the same problem. Travel faster than light to a distant star. From certain reference frames, you arrive before you left. Stay a while. Travel back faster than light. You could return to Earth before you departed. Meet yourself. Prevent yourself from leaving. Paradox. Physics appears to prohibit faster-than-light travel, specifically to preserve causality. Light speed is the maximum velocity at which cause can propagate to effect. Exceed this speed, and the temporal order of events breaks down. The universe becomes logically inconsistent. Every experiment confirms this boundary. Particle accelerators push particles to 99.999991% light speed. Never faster. Quantum entanglement creates correlations faster than light, but cannot transmit information faster than light. The cosmic speed limit holds absolutely. Some physicists have proposed solutions. Wormholes that connect distant points in spacetime. Alcubierre drives that warp space around a spacecraft. These might allow apparent faster-than-light travel without actually moving through space faster than light locally. But they require exotic matter, negative energy, things that may not exist. Even if exotic matter exists, these solutions face causality problems. A wormhole could become a time machine. Enter at one end, exit at the other, in your own past. The universe might prohibit this through quantum effects. Hawking's chronology protection conjecture suggests the laws of physics prevent time travel by generating destructive feedback. The intimate connection between light speed and causality is profound. Light speed isn't just a velocity. It's the rate at which cause and effect propagate through spacetime. It's the speed of causality itself. This is why nothing can exceed it. The logical structure of reality depends on this limit. Without the light speed limit, physics becomes inconsistent. Time ordering depends on reference frame. Different observers disagree on cause and effect. Paradoxes proliferate. The universe becomes impossible to describe mathematically. Relativity and causality together enforce the cosmic speed limit. Every GPS satellite proves this daily. Every particle accelerator confirms it billions of times. Every precision clock experiment verifies it. Light speed is the guardian of causality. Break this speed, and you break logic itself. But GPS satellites prove relativity in another way. One so practical that billions of people depend on it working correctly every single day. Your phone knows your location because engineers account for Einstein's predictions. And without relativity corrections, your navigation would fail within minutes. 24 satellites orbit Earth at 12,430 miles altitude. Each carries multiple atomic clocks, synchronized to within a few billionths of a second. These satellites broadcast signals containing precise timing information. Your phone receives signals from 4 or more satellites and calculates your position. The calculation depends on light speed being constant. The phone measures how long each signal took to arrive. Multiply travel time by light speed, and you get distance to each satellite. With distances to 4 satellites, The phone triangulates your exact position. Simple geometry. But there's a problem. The satellites are moving at 8,750 miles per hour relative to Earth's surface. Special relativity predicts their clocks should run slower than ground clocks. Time dilation. At this velocity, satellite clocks lose about 7 microseconds per day. The satellites also orbit in weaker gravity than Earth's surface experiences. General relativity predicts clocks run faster in weaker gravitational fields. This effect adds about 45 microseconds per day. Net effect. Satellite clocks gain 38 microseconds per day compared to ground clocks. 7 microseconds lost from motion. 45 microseconds gained from altitude. 38 total gained. How much does this matter? Light travels 1 foot per nanosecond. 38 microseconds equals 38,000 nanoseconds. In 38 microseconds, light travels 38,000 feet. That's over 7 miles. If satellite clocks drift by 38 microseconds, position calculations are wrong by 7 miles. After 1 day without corrections, GPS errors would reach 7 miles. After a week, 50 miles. After a month, over 200 miles. The system would be completely unusable. Your phone would tell you you're in the next city when you're actually at home. GPS engineers faced this problem during system design in the 1970s. Some argued relativistic effects were too small to matter. Others insisted corrections were essential. Debate continued. Finally, they decided to include the corrections. The solution is elegant. Before satellites launch, their atomic clocks are programmed to tick slightly slower than ground clocks. The rate is adjusted by exactly the amount general relativity and special relativity predict. When satellites reach orbit, relativistic effects speed their clocks up to the correct rate. The clocks then stay synchronized with ground time. Every GPS satellite in orbit has been adjusted for relativity. Remove those adjustments, and the system fails. This has been tested. Early satellites included the ability to switch relativistic corrections on and off. With corrections off, positions drifted exactly as Einstein's equations predicted. This means every time you use Google Maps, you're proving relativity. Every Uber ride, every GPS-guided aircraft, every surveyor, using precision positioning, billions of position calculations daily, all confirming special and general relativity. The corrections aren't approximate, they're precise. The math matches Einstein's equations exactly. Slight changes to the correction factors would cause position drift. The exact values predicted by relativity are required. No other values work. Other satellite navigation systems confirm this independently. Russia's GLONASS, Europe's Galileo, China's Beidou, all include identical relativistic corrections. Different orbital altitudes means slightly different correction magnitudes, but the same physics applies. Every system verifies relativity. The International Space Station experiences similar effects. At 250 miles altitude, orbiting at 17,500 miles per hour, astronauts age about 7 microseconds less per day than people on Earth. Not much, but measurable with atomic clocks. The effect exactly matches special relativity predictions. Commercial aircraft also experience measurable time dilation. At cruising altitude and speed, atomic clocks on planes gain about 20 nanoseconds per hour. Not enough to affect any practical application, but measurable, and it matches theory perfectly. GPS isn't abstract physics. It's not a laboratory curiosity. It's working technology used by billions of people daily. The fact that it works proves relativity is correct. The fact that corrections must be precise proves Einstein's equations are accurate. Your smartphone is a relativity experiment. Every position fix confirms that time dilation is real. That clocks run at different rates depending on motion and gravity. That Einstein was right about the structure of spacetime. Without relativity, modern navigation would be impossible. We'd be back to using paper maps and compasses. GPS demonstrates that special relativity isn't just theory, it's practical physics that technology depends on. But GPS corrects for small relativistic effects at modest speeds. What if we could somehow bypass the speed limit entirely? What if there were loopholes in the laws of physics? Some spacetime. Inside the bubble, you're not moving faster than light locally. Space itself isn't moving faster than light relative to you. But the bubble carries you across vast distances faster than light could traverse them externally. You sidestep the speed limit by warping space-time geometry. The math works within general relativity. Alcubierre wrote down equations describing this space-time geometry. It's consistent with Einstein's field equations. On paper, it's possible, but there's a massive problem. The drive requires exotic matter with negative mass-energy density. Negative mass means gravitationally repulsive matter. Instead of attracting, it pushes away. Nothing in nature has negative mass. We've never observed it. We don't know if it can exist. The standard model of particle physics doesn't include it. Creating the Alcubierre bubble would require amounts of negative mass energy comparable to the mass of Jupiter. Even if negative mass exists, collecting Jupiter mass quantities is impossible with any conceivable technology. And that's just one problem. The bubble might accumulate particles at its edge. When you decelerate, all that accumulated energy could release catastrophically. You'd incinerate everything at your destination. Wormholes are another theoretical possibility. Solutions to Einstein's equations that connect distant points in spacetime. Enter one end, exit instantly at the other end, perhaps thousands of light years away. You never travel faster than light locally, but you traverse vast distances quickly by taking a shortcut through spacetime itself. General relativity permits wormholes mathematically, but stable, traversable wormholes require exotic matter to hold them open. Without negative mass energy, wormholes collapse faster than light can cross them. They pinch shut before anything can travel through. Even if you had exotic matter, creating a wormhole might be impossible. You'd need to manipulate spacetime on scales far beyond current technology. Quantum effects might destroy any wormhole before it becomes useful. Hawking radiation could make traversal lethal. Some wormholes could become time machines. Connect two wormhole mouths. Move one at high velocity. Time dilation makes the moving mouth age slower. Now, the two ends exist at different times. Enter one, exit at the other, in the past. This creates causality problems. The universe might prevent this through quantum effects. Quantum entanglement offers a different avenue. Entangle two particles. Separate them by vast distances. Measure one and the other's state instantly changes. The correlation happens faster than light. But you can't use this to transmit information. The receiving end sees random results until they compare notes, which requires normal, slower than light communication. Some physicists proposed using entanglement to send signals. Every attempt fails. Quantum mechanics prevents information transmission faster than light through entanglement. The universe seems to have a built-in protection against causality violations. Tachyons are hypothetical particles that always move faster than light. If they exist, they'd have imaginary mass. Their equations require them to speed up when losing energy. They'd experience time backward. No experiment has ever detected tachyons. Most physicists think they don't exist. Every proposed loophole requires violating known physics. Exotic matter we've never seen. Negative energy we don't know how to create. Quantum processes that might be impossible. Space-time geometries that may not be stable. None of these solutions are practical. Most are probably impossible. The universe seems determined to enforce the light speed limit. Every attempt to find a loophole runs into problems. Physical impossibilities, logical paradoxes, quantum barriers. As if reality itself actively prevents faster than light travel. Perhaps the real barrier isn't engineering. Perhaps it's fundamental. The structure of spacetime might simply not permit faster than light travel in any form. All the proposed loopholes might be mathematical curiosities that can't manifest in reality. But even if loopholes existed, even if we could somehow exploit them, there's one more problem that makes relativistic travel terrifying. One we haven't discussed yet. The only path around light speed's barrier requires a substance that has never been observed, might not exist, and if it does exist, would violate nearly everything we understand about matter and energy. Exotic matter sounds like science fiction terminology, but it's a precise physics concept. Matter with negative mass energy density. Not antimatter, which has positive mass. Not dark matter, which also has positive mass. Truly negative mass that generates gravitational repulsion instead of attraction. Every proposal to bypass light speed requires exotic matter. Alcubierre drives need it to warp spacetime. Wormholes need it to stay open. Even some quantum-based schemes require negative energy states. Without exotic matter, these loopholes close. With it, they might barely open. What would negative mass do? Push instead of pull. Place negative mass near Earth, and it would fall upward, accelerating away from the planet. Earth would also accelerate toward it. The two would chase each other forever, accelerating continuously. This violates intuition completely. Push negative mass, and it accelerates in the opposite direction you push. The harder you push, the faster it moves away from the force. This seems to violate Newton's laws. Force equals mass times acceleration. Negative mass means force and acceleration point opposite directions. Conservation of energy becomes strange. Positive and negative masses interacting could generate unlimited energy. The system accelerates indefinitely. Total kinetic energy grows without bound. Where does this energy come from? The equations suggest it appears from nowhere. Has anyone ever observed negative mass? No, not once, not even hints. Every particle we've detected has positive mass energy. Photons have zero rest mass, but positive energy. Neutrinos have tiny positive mass. Even the Higgs boson has positive mass. The universe seems to exclusively produce positive mass energy. The Casimir effect creates something similar to negative energy. Place two metal plates extremely close together in vacuum. Quantum fluctuations between the plates are restricted compared to outside. This creates a pressure difference. The plates attract. You could interpret this as negative energy density between the plates. But the Casimir effect is minuscule. The force between plates a few micrometers apart is measured in nanonewtons. To power an Alcubierre drive, you'd need negative energy density, trillions of times stronger. We don't know how to amplify the effect. We don't even know if amplification is possible. Some quantum field theory solutions permit negative energy density temporarily. But quantum inequalities restrict how much negative energy can exist and for how long. The more negative energy, the shorter duration it can exist. The product of magnitude and duration is bounded. This might prevent macroscopic exotic matter from existing. Creating large amounts of exotic matter might be fundamentally impossible. Quantum mechanics might forbid it. Attempts to concentrate negative energy could trigger vacuum decay or other catastrophic processes. The universe might have built-in safeguards against exotic matter accumulation. Even if exotic matter exists and we could create it, controlling it seems impossible. How do you contain matter that's gravitationally repulsive? Ordinary containers push it away. Magnetic fields don't work on uncharged exotic matter. You'd need exotic forces to control exotic matter. Storage would be nightmarish. Exotic matter would accelerate away from any containment. It might be fundamentally uncontainable. The moment you create it, it escapes. Using it to warp spacetime requires precise placement and control. If you can't even hold it in place, how can you use it? The energy required to create exotic matter is unknown, but probably enormous. Warping spacetime significantly requires tremendous energy density. Creating Jupiter-mass quantities of exotic matter might require more energy than exists in the solar system. We're not just talking about difficult. We're talking about possibly beyond the total energy budget of any civilization. Theoretical physics papers discussing exotic matter usually include disclaimers. These solutions are mathematically interesting, but may not correspond to physical reality. The equations permit exotic matter, but nature might not. Mathematics allows many things that physics forbids. Some physicists argue exotic matter is impossible on fundamental grounds. Others think it might exist but be inaccessible to technology. A few optimists suggest we haven't looked hard enough. But after decades of searching, we've found nothing. No evidence, no hints, no experimental signatures. Without exotic matter, all faster-than-light schemes collapse. The loopholes close. We're back to the hard speed limit. The universe enforces its cosmic speed limit not just through relativity, but by denying us access to the only materials that might bypass it. But there's one more reason relativistic travel is dangerous, beyond just the impossibility of reaching light speed. Something that makes even 90% light speed incredibly hazardous. At near light speed, hitting a speck of dust releases energy equivalent to nuclear weapons, and space is full of dust. Space seems empty, dark, void, but it's not perfectly empty. There's matter everywhere. Gas molecules, dust grains, micrometeorites, atoms of hydrogen scattered throughout interstellar space. About 1 atom per cubic centimeter on average. That doesn't sound like much. It's deadly at relativistic speeds. A single proton has a rest mass of about 1.7 times 10 to the negative 27 kilograms. Essentially nothing. But at 99% light speed, that proton carries kinetic energy amplified by the Lorentz factor of 7. Its impact energy is 7 times larger than its rest mass energy. Calculate the numbers. One proton at 99% light speed carries about 10 million electron volts of kinetic energy. That's 10 million times more energetic than the same proton at rest. Cosmic rays consist of these high-energy particles. They hit Earth's atmosphere constantly. Individual protons don't cause much damage, but a spacecraft moving at 99% light speed encounters quadrillions of them per second. Your spacecraft has frontal area, maybe 10 square meters. As you travel 1 light year, you sweep through a cylinder of space 10 square meters in area, and 1 light year long. That cylinder contains about 10 to the 17th atoms, 100 quadrillion atoms. Each atom hits you with energies comparable to cosmic rays, individually manageable, collectively devastating. The integrated dose of radiation would be enormous. Shielding would have to stop quadrillions of high-energy particle impacts, but atoms are just the beginning. Dust grains are worse, much worse. A dust grain massing 1 microgram, smaller than a grain of sand, carries staggering energy at 99% light speed. Calculate the kinetic energy, half the Lorentz factor times mass times light speed squared. The answer is about 300 trillion joules. That's 70 tons of TNT. One tiny dust grain, smaller than a pinhead, releases energy equivalent to a small tactical nuclear weapon on impact. The collision would vaporize the grain instantly. The expanding plasma would blast through your spacecraft hull. Metal would evaporate. Structure would fail. The ship would suffer catastrophic damage from a single microscopic particle. Larger particles are devastating beyond description. A pebble massing 1 gram at 99% light speed carries 300,000 trillion joules. That's 70 megatons. Larger than the biggest nuclear weapon ever detonated. One pebble destroys your entire spacecraft, vaporizes it completely. Nothing remains. The odds of hitting larger particles increase with distance traveled. Space isn't uniformly distributed. There are denser regions, molecular clouds, debris from stellar winds, interstellar dust concentrated along the galactic plane. Navigate through these regions and you're flying through a minefield. At 99.9% light speed, kinetic energies multiply by another factor of 3. Now a dust grain releases over 200 tons of TNT equivalent. A pebble yields 200 megatons. The faster you go, the more catastrophic any collision becomes. Could you shield against this? Solid armor won't work. The impact energy vaporizes any material. The plasma jet penetrates deeply. You'd need meters of armor, making the spacecraft impossibly massive. And the armor itself becomes a problem. High-energy impacts generate secondary radiation that floods the interior. Magnetic shields might deflect charged particles, but dust grains are electrically neutral. They pass through magnetic fields unaffected. You'd need fields strong enough to ionize approaching particles, then deflect the ions. The power requirements are enormous. The fields would have to extend far ahead of the ship. Some have proposed ablative shields, layers of material that vaporize on impact, absorbing energy. But at relativistic speeds, ablation can't dissipate enough energy fast enough. The impact happens faster than material can respond. Shock waves propagate through the shield at the speed of sound in the material. The impact is traveling at 99% light speed. The shield can't react in time. Active defense seems impossible. You can't detect and avoid individual dust grains at near light speed. They're microscopic. Radar can't resolve them. By the time you detect anything, you've already hit it. Light from an approaching particle only reaches you nanoseconds before impact. No time to maneuver. Every collision generates X-rays and gamma rays. High-energy photons flood your spacecraft. The crew receives lethal radiation doses. Electronics fail. Materials degrade. The ship slowly disintegrates under constant bombardment, even if no single impact is catastrophic. Natural cosmic rays don't damage us because they're individual particles. We don't collide with them at relativistic speeds. They collide with us. The relative motion is what matters. But a spacecraft at relativistic speed effectively turns every particle in space into a cosmic ray from the spacecraft's perspective. Some calculations suggest that at 99.99% light speed, flying through the interstellar medium generates radiation equivalent to flying through a nuclear reactor core. The dose rate would kill humans in minutes. Shielding heavy enough to protect against this would make the spacecraft too massive to accelerate. This problem has no obvious solution. It's not engineering. It's fundamental physics. Kinetic energy scales, with velocity squared, in the classical limit, and grows even faster relativistically. Eventually, collision energy exceeds any material's ability to withstand impact. Even the best proposed designs for relativistic spacecraft include massive forward shields, multiple layers, sacrificial ablation, magnetic deflection. But no design convincingly solves the problem at extreme relativistic speeds. The energy of collisions simply becomes too large. But maybe future physics will discover solutions. Maybe new theories will reveal possibilities we haven't imagined yet. Could quantum gravity rescue relativistic space travel? Einstein's relativity is incomplete, and the theory that replaces it might reveal new possibilities or slam the door on light-speed travel even more firmly than current physics. General relativity describes gravity beautifully. Space-time curvature, black holes, gravitational waves. Every prediction confirmed. But the theory has limits. It breaks down at quantum scales. Inside black holes, at the Big Bang singularity, where gravity becomes extremely strong and quantum effects matter, general relativity fails. Quantum mechanics describes the other three fundamental forces perfectly: electromagnetism, strong nuclear force, weak nuclear force. All are quantum field theories. They work at the smallest scales. But gravity resists quantization. Combining general relativity with quantum mechanics produces nonsensical infinities. Physicists have searched for quantum gravity for decades. String theory is one approach. Loop quantum gravity is another. Dozens of other proposals exist. None have experimental confirmation. We don't know which, if any, is correct. We don't even know if a unified theory is possible. Why does this matter for light speed travel? Because quantum gravity operates at the Planck scale. Distances of 10 to the negative 35 meters. Times of 10 to the negative 44 seconds. Energies of 10 to the 19th giga-electron volts. At these scales, spacetime itself might be quantized, discrete rather than continuous. If spacetime is quantized, light speed might emerge from deeper principles. The speed limit might be a consequence of spacetime's granular structure, or it might be negotiable under extreme conditions. We don't know. Quantum gravity could change everything or change nothing. Some quantum gravity theories suggest spacetime has fundamental limits. You can't probe distances smaller than the Planck length. You can't measure times shorter than Planck time. These limits might impose absolute constraints on motion. Light speed might be more fundamental than relativity suggests. Other theories propose extra dimensions. String theory requires 10 dimensions. M theory requires 11. Most are curled up microscopically, but if we could access them, physics might work differently there. Light speed in extra dimensions might have different values. Traveling through extra dimensions might allow bypassing the normal speed limit. But this is pure speculation. No experimental evidence supports extra dimensions. They're mathematical requirements of certain theories. Whether they physically exist is unknown. Whether we could access them is even more uncertain. Some physicists suggest that at Planck energies, spacetime itself becomes unstable. Quantum fluctuations dominate. Virtual black holes appear and disappear. The smooth spacetime of general relativity becomes a foaming quantum structure. In this regime, normal concepts of distance and time might not apply. Could this offer a loophole for faster-than-light travel? Maybe, but probably not. More likely, quantum effects just make spacetime more complicated. The speed limit remains. It might even become more stringent. Quantum corrections could strengthen the barriers rather than weakening them. Hawking radiation shows one way quantum effects change general relativity predictions. Black holes aren't perfectly black. They evaporate slowly through quantum processes. Something similar might affect other general relativity solutions. Wormholes might quantum evaporate. Alcubierre bubbles might quantum decay. Quantum gravity could eliminate all the proposed loopholes. We're far from understanding quantum gravity. Experiments at Planck energies are impossible with any conceivable technology. The Large Hadron Collider reaches 10 to the 4th giga-electron volts. Planck's scale is 10 to the 19th. We'd need particle accelerators larger than the galaxy. Direct testing is beyond reach. Indirect evidence might come from astrophysics, gravitational wave observations, black hole shadows, cosmic ray behavior at extreme energies. These observations might reveal quantum gravity effects. But so far, general relativity matches all observations. If quantum corrections exist, they're too small to detect currently. The ultimate theory of physics might reveal possibilities we haven't imagined. New symmetries, new dimensions. Universe genuinely forbids faster than light travel at every level. Classical mechanics said no. Special relativity said no more firmly. General relativity offers tempting loopholes that seem to require exotic matter we can't create. Quantum gravity might say no most firmly of all. The final answer awaits a complete theory of quantum gravity. Until then, we work with the physics we have, and the physics we have says no. Light speed is the ultimate limit. Nothing with mass can reach it. Nothing can exceed it. The universe enforces this rule through multiple mechanisms: energy requirements, momentum growth, time stopping, length vanishing, causality protection. Every experiment confirms the barrier. Every GPS satellite, every particle accelerator, every cosmic ray detector, every atomic clock. The evidence is overwhelming. The speed of light stands as the ultimate boundary between what's possible and what forever remains beyond reach. We've explored every angle: the mathematics, the experiments, the technological challenges, the fundamental physics. All roads lead to the same conclusion. Light speed travel for massive objects is impossible. Not difficult, not expensive. Impossible. The universe says no.